Good afternoon, everybody. Good morning for someone. So it's a pleasure today to have here Jacqueline Reis, Microelectronics Director of IDEA, to talk about the microelectronic ecosystem in Brazil from the IDEA's perspective. So Jacqueline Reis has over 12 years of experience in optical communications, focusing on high-speed optical transmission, networking, and digital signal processing. He, as a microelectronics director, he leads more than 40 top engineers developing signal processing ASICs for optical transceivers in deep submicron nodes. You are going to see that they are doing designs in 7 nanometers. He worked at the CPQD Foundation as a research and development specialist, leading another important group. He worked at BR Photonics in 2017 as an optical system manager focusing on optical system modeling and DSP IP cores development. He has undergrad in 2006 and master in 2007 in electrical engineering from the Federal University of Pará, and the PhD degree from University of Aveiro. By the way, the library of the University of Aveiro is a very nice one, designed by the Portuguese architect Álvaro Siza, that is the same architect that has done the Iberê Camargo Museum at Porto Alegre. So I think Jacqueline agree with me, that's a very nice library. So he has published more than 150 scientific papers in the field, including top conference in highly ranked journals, more than 900 citations, and he is an IEEE and OSA member, highly active in industrial forums and standards, and has filed already 8 patents. So thank you very much, Jacqueline, to accept our invitation here. So just for some ones that saw the first flyers that the talk would be done by Julio, but for the logistic reasons, he was not able in the last moment, and Jacqueline will do the presentation in name of on behalf of IDEA today. So thank you very much, and I'm going to give the floor to you to start your presentation.
Thank you.
It's being done, so you have the control of the slides now.
Thank you, Professor Reis. I also would like to, in the name of IDEA, to acknowledge and thank the IEEE CAS for the invitation and giving us this opportunity to present a little bit of our view and our evolution, focus on microelectronics here in Brazil. So we are very glad to be able to share a little bit of our company and what we are doing in the field of microelectronics. And we appreciate the invitation. So the discussion today that we'll try to share with you guys that are online and watching this webinar, we will try to present in these following minutes a little bit of some activities that we are doing, what our company is doing. Our partners that work with us here in Brazil, and we also have lots of partners around the world. And please feel free to ask anything that you'd like during the discussion. So to start, I would like to share this view to try to explain why we do what we are doing today here at IDEA. So I also would like to apologize for the slide. It's a little bit lots of information on it, but I'll try to walk you through, starting here from the bottom left. So basically, in IDEA, what we have today, we have 3 main technological platforms. We have the product engineering area that's trying to converge all the devices and the development, all the R&D program that we do with a product view. We also have the photonics division that focus on developing all the photonics devices such as lasers and photonics IC. I will walk you through a little bit more in the coming slides. And we also have the microelectronics division that will be the main focus of our discussion today. But those three technological platforms that we have an idea, and we have been working with our partners to develop this expertise and this knowledge, we are mainly trying to focus on solving the problems of connectivity. So we understand, and I think today, based on the situation that we are living nowadays, we can see how important and how reliable communication technology systems should be, especially for the world that we are living today, that require lots of connectivity among people, between people and machines, and between machines. So what, of course, for us to try to provide what we are doing today in terms of technology and really see the end result in the society, it takes some time to, let's say, to what we are doing here at IDEA and any other company that do R&D on ICT. So it's a long path until we get the result and the society can benefit of what we are doing. But we understand that in order to do that, so that what we are doing today and how to see this impact on the society, we cannot do by ourselves, right? So we depend, of course, on this ecosystem that we have different tiers until you get your technology becoming a product, and then this product getting to the end result, and then, of course, generating value to the society. So in our case, it's not different. So we have a partner that is in the US, and what we do here with this partner is basically to take all this technology that we are developing on the microelectronics, photonics, and product engineering, and try to develop this product here that we are calling the optical module. It's basically the main device that will be used to enable very high-speed telecommunication systems. So this optical module is basically the optical transceiver that performs optical to electrical conversion and electrical to optical conversion. And this device, this optical module, it basically deploy in those equipments, in those telecom equipments that we are calling the switch Ethernet. This switch Ethernet is basically the main equipment that, let's say, is deployed inside those hyperscaler data center that we have today. So this type of trend, these hyperscaler data centers, basically they acquired they arrived in this ecosystem with very strong and very different requirements that we were used before. So in previous optical communication systems, most of the time we were working for requirements to be able to deploy telecommunication systems so that the telecom operators could deploy their connectivity services like internet, TV broadcasting, telephone connectivity, and so on. But today, we have seen that those hyperscaler data centers companies such as Microsoft, Amazon, Google, Facebook, Apple, Alibaba, and so on, they have acquired a very, let's say, a very demanding requirement and very different than we were before. So today, all the technology that IDEA is working on is try to focus on those demands that will enable interconnection between those hyperscaler data centers. And those requirements, they are very challenging. So this type of companies, what they try to do, they try to promote this interoperability, meaning that all the equipments and all the technology that we are working at IDEA interop among different vendors. So that's a very challenging requirement. And also they come with these requirements for very high volume application, for very low power consumption. And of course, this puts some stress on the engineering level in order to use the best what we have in terms of technological tool to try to develop those components. And in the past, we were much more focused on providing technology for those type of companies, those system companies that work with the telecom operators. Like here in Brazil, we can mention, for instance, Vivo, Oi, TIM, and among others, where basically they didn't have those kind of requirements in terms of high volume, interoperability, power consumption, and so on. They were much more focused on performance, whereas for this type of applications to allow data center interconnection, we are much more focused today on interoperability and high volume and low cost for those components. So this is the path that we follow, right? So together with our US partner, we work to develop these optical modules. Then therefore is integrated in these components that we are calling the optical switches that provide the Ethernet connectivity inside the data center, and those equipments are then deployed inside the data centers. So this is the path that we follow, that our technology follows until we get the impact and we provide the value for the society. But of course, we are not the only company doing this in the world. I could give a few examples of other companies trying to doing the same thing as we are doing at IDEA. So here I can mention Acacia, Inphi, NDT Electronics, and NeoPhotonics. Those also are companies that are trying to develop this technology to solve this problem, this challenge, to provide the technology to allow, let's say, data center interconnection. This is this is a very, let's say, very challenging ecosystem, because we have very tough competitors with a market cap very. Most of those companies, they are companies listed on NASDAQ, or also in on the market. So they have a very, let's say, very high market capitalization, and those are and that's why what we are doing here at IDEA is very challenging, because we have those very challenging requirements, but also those very tough competitors that are working to try to solve the same problems as we are doing. But the good thing, I would say, that what, let's say, differentiate us in terms of technology here in Brazil is we take advantage of this very interesting ecosystem that we have available here in Brazil. Because we have to tackle both the microelectronics, the photonics, and the product engineering, we have to look for people that are willing to challenge this kind of technology. And although I'll talk a little bit more about microelectronics today, but in IDEA we have a multidisciplinary team that can also work with mechanics, thermal analysis, photonics, as I said before, optical packaging, module assembly, fiber routing, hardware design, embedded software engineering, and automated test. All of those components, or all of those expertise are needed to develop the optical transceiver module that I explained before. And of course, we have to develop a state-of-the-art microelectronics VLSI flow in order to meet those requirements that we have for those kind of applications that we are dealing. So basically, I will try to focus a little bit more about on what this device is that goes inside the optical module. What is a coherent DSP ASIC? That's a microelectronic device. Why this is so challenging to to develop this kind of device, especially in our ecosystem here in Brazil. So basically, every time that the information travels through the optical fiber, all this information suffers different physical impairments. So when we do the conversion of the electrical domain to the optical domain, we already have some impairments that will basically needed to be reconstructed in terms of the information that will be transmitted over the optical fiber. So the optical fiber itself, it's a nonlinear channel. We have lots of impairments there, such as chromatic dispersion, amplified spontaneous emission noise. We also have polarization, mode dispersion. All of those effects, they basically destroy all the information that we are transmitting over the fiber. And of course, we should have this electronic device that will perform a series of digital signal processing in order to reconstruct this information. So basically, the main purpose of this device is basically to tackle those physical impairments that will destroy the information as soon as we transmit this over the optical fiber. The other thing is that the capacity in terms of signal processing is huge for this type of application. So we are talking about links that can go from 100 gigabit per second all the way to 800 gigabit per second. And of course, this requires us to use state-of-the-art technology for the CMOS processing that we will use to develop those application-specific integrated circuits. This is also an SoC that has a very high density digital core with a very high speed analog converters. So just to give you an idea, we are talking about here signal content that can span from 30 gigabaud all the way to 100 gigabaud. And in order for us to be able to recover this kind of information, we should sample the signal in those converters on the orders of 100 to 200 gigasamples per second. So that requires us to use the best that we have available for the industry. So just to give you an example, those type of devices today, we are able to integrate hundreds of millions of transistors. Depends on the application that we are trying to support. We use CMOS FinFET technology from 16 nanometer. This was back in 2018. The first products were launched using this kind of technology for the application of coherent DSP ASICs. To this year and the next year, we will see the first products already using 7 nanometer and 6 nanometer for the CMOS technology. And probably for the coming year, next year, we will see the first prototype devices using 5 nanometer and so on. So as I said, this device, that it goes inside the optical module, it basically performs modulation and demodulation for digital modulation, such as quadrature amplitude modulation and phase shift keying. Those are the kind of digital modulation that we use to transmit the information of the optical channel. We also perform static equalization and dynamic equalization to recover the information that is basically affected during the transmission of the optical fiber. We also perform channel coding in order to enhance the robustness of the transmission information that we use. And we also perform all the network protocol and framer on the host side in order to allow us to plug this type of device in a switch Ethernet that can be deployed inside the data center or inside telecom operator. So this is those are the main functionalities that we perform here. So we're starting from the line side that basically connects this device to the optical fiber, all the way to the host side where we have the pluggable part of this module connected in this Ethernet equipment that goes inside the data center. This is basically an overview of the flow that we follow and that we have been developing inside IDEA. So we started with these requirements that we discuss and we try to understand with our customers. We also attend, as Professor Hayes mentioned in the introduction of this talk, we attend different industrial forums to try to understand a little bit more the marketing needs and how how the industry is trying to converge for very, let's say, interoperable requirements. So we work with our customers and our partners to try to understand a little bit more on those requirements. After that, we do what we call spec and modeling phase, where we will basically try to provide some guidance to our customer in terms of technical feasibility. So we at this part inside the flow, we start to mature those requirements and understand and put some numbers on those requirements to provide some feedback to our customers, just so that we are following the right path to tackle their needs. So here we are not talking about yet on the transistor level. We are basically trying to understand a little bit more the requirements and the functionalities. Then we start the design phase of the microelectronic device. We started, as any other company, with the logic design. This logic design basically try to translate all the high-level modeling that we are doing here in this spec and modeling phase. We try to put now, in this case, the hardware requirements, what kind of clock that will reach, what kind of parallelism that we will use, what is the power dissipation that we have, what is the latency, how this let's say, this microelectronic device will work in order to meet and to tackle all the functions that we have to do in order to enable this type of application that we are discussing. So basically here we work with team, what we are calling the front end in the VLSI flow. So we work with both the hardware description language to start put the architecture together to meet the requirements that we defined before, and we work very closely with the verification team. So this logic design follows in two paths, right? In the one that we are looking at the hardware description language design, and also on the verification team to try to understand what are the requirements of the circuit design, and see that if this circuit design that we are doing meets the requirements of the application that we have defined before. So here we start putting, although we work at the RTL level, the hardware description language level, but we also do lots of logic synthesis to try to understand what is the specificities of the process that we will use to feedback these digital circuits that we design, and see if we are closing time, with the size of the circuit is okay and can be physically designed in the next phase. So here basically we go from function design, all the functions that we will do, we design the RTL, we synthesize this RTL, we verify this RTL using concepts such as UVM, automated test bench, and this verification is done at both RTL and netlist level. Then we go to the physical design. So in this physical design, it's where we start to put all this architecture together, but in a physical view. So we do all the physical floor planning of this chip. So we define the area of the chip, the partition of those physical blocks that we integrated here. We do some very quick place and route in order to provide some feedback for the logical design team to make sure that, okay, the circuit can meet time, we can place this circuit, and also routing and close time among the different physical blocks that will have different sizes within the circuit. So this is, and here, this design is very, let's say, dependent on the process that we are doing. So we have done circuits at 28 nanometer that have some requirements to close time, but then when we go to 16 nanometer and 7 and 6 nanometer, the requirements change quite significantly. And again, this team, this physical design team, is the one that is most specialized for the process that we are using. So we work very closely with the foundry to understand the requirements and also the IP providers that we will use in order to have this design physically done. So after we close this physical design, we basically move to the tape-out phase, where we interact a lot with the foundry. We try to understand what can be waived and what has to be fixed in order to have the design ready for production. And in parallel, we also work with the companies that will design the package of this device, because although we do not design the packaging itself, this GDS that we send to the foundry at die level has to be integrated in a package so that can allow to be deployed in the product. So that's the flow. And after we taped out this chip, we have silicon back. We work also with our partners to validate this device in the lab. So that's basically what we have in our flow. So we work all the way from the requirements to the spec modeling phase, logic design with verification, physical design with physical verification, work on the integration, send the final GDS to the foundry to be produced, work with the packaging house to understand the requirements and make sure that the die that we design will achieve the performance that we'll have in the product in the end. So that's a quick overview of our flow. I will just summarize some of the chips that we have designed in the past. I have to emphasize that this is a collaborative work. So as I mentioned before, IDEA has several partners that help us going through all those devices that we are designing. So just to give you an example, so our first chip that we designed, we used 28 nanometer process. This chip was designed to support 100G DPQ PSK applications. So basically, this chip was designed to support WDM transmission from 80 kilometers all the way to 2,000 kilometers. So it's basically a 100 gigabit Ethernet transponder. And this device has an 8 millimeter square. We have around 30 million standard cells that we used in this device. This chip was designed, was taped out around 2018, and after that we moved to this new process, 7 nanometer. So we started working in 7 nanometer process back in 2017, Q4 2017. Our first goal was try to work with this process, was try to first validate some of the IPs that we have designed before, but mostly the flow that we used in the 28 nanometer project. So it was very challenging for us to work with this technology. The PDK back then was not so mature. So we had to interact a lot with the foundry to understand the requirements, to understand how the process was working and being validated, and take the most advantage of this process. So our first tape out with this process was back in 2018, around September, where we include some DSP function. It was a test chip that had some DSP functions and some diagnostic memory to allow us to put data inside the chip, capture those data and process to check to check if this function was implemented correctly. And as I said, it was mainly to validate our 7 nanometer flow and also the power consumption measurement and to try to correlate what we were seeing, what we are estimating in terms of power consumption during the implementation flow, and also what we were measuring at the silicon. Last year, beginning of last year, we had our second tape out in this process, in this 7 nanometer process, where we used the same technology, 7 nanometer FinFET. It was a test chip as well with around 600K standard cell, which can be extrapolated to around 50 million transistors. with lots of memory inside the chip to also allow us to do playback and capture of data. And this IP was developed essentially to validate some DSP functions to allow very short reach application for common electrical interface at 112G. So this kind of IP is deployed inside the SerDes that are used inside of those DSP coherent ASICs. And then we had this this program to work on a 400G DSP ASIC chip, also in 7 nanometer. This design was, of course, much bigger than those previous one here. We had a 50 millimeter square silicon with more than 50 million cells, which give us around 200 million transistors inside this chip to support applications of WDM transmission as well, but 400ZR data center interconnection. So this is basically a 400 gigabit Ethernet transponder. And since last year, we were working on this device in another process. This is now 6 nanometer FinFET. It's to support the same application, 400G ZR, but in this case, it's a much more reduced device with 26 millimeters square, but with the same cell count, around 50 million and 200 million transistors. And this is what we are working today, and we are expecting to send to the foundry this year for production. So this is what we have to present to you about what we are doing in terms of microelectronics at IDEA. And just to share a little bit more with you, so we are a research and development company focused on information technology. We try to address this global market. So all those applications, most of those applications that we are developing today, they are to meet those requirements for those companies that are not in Brazil, but we understand that what we are doing today will have an impact in Brazil in the future because it's the same technology that will be deployed in the next following years. Basically, what we try to promote inside IDEA is basically this convergence between photonics and microelectronics with a clear view on the products that will be deployed in those telecommunication systems. So we work very closely, as I mentioned to you, in this microelectronic, photonic, and product engineering to try to streamline all the methodology that we are doing to enable a very high quality products working together with our customers. So we are based in Campinas, here in the state of São Paulo. We have 2 main locations today. That's inside the Unicamp, the State University of Campinas. We had today those 2 engineering offices that we have around 60 engineering team working with us among some partners that we have spread in Brazil and in other countries. We also are equipped with clean rooms to do all the validation of the devices that we are producing, both microelectronics and photonics device. We also have some capability to do all the engineering for inside the optical modules to do qualification and to provide those devices very close to the production for our customer. This is our ecosystem. As I mentioned before, we do not believe that by ourselves inside the IDEA we will be able to tackle all those challenges that we have. So in this case, we work with different kind of partners from university, R&D centers, and companies that work together with us to understand our demands and to allow us and to help us develop the flow that we use inside IDEA, but also providing some infrastructure. So we try to work in this business model where all the CapEx are work together with our partners, and we try to focus specifically on the development of the human resources assets, because this is what we believe it's very important at this stage of the technology that we are doing. And this is just to give you an idea where we have partners. So as I said, we are here in Campinas, but we have partners inside Brazil, in Florianópolis, in Campina Grande. We also have here in Campinas, inside the university, the State University of Campinas. We have CPQD, which is a research and development center here in Campinas, and also Instituto Eldorado, which is another research and development team, research and development center based here in Campinas. And besides that, we have companies working with us in Argentina, in Portugal, in the US, and those are the main, let's say, partners that we have today. So yeah, I think this is what we have prepared for you today. And Professor Reis, I'm open to any questions that you may have, and I feel free to give you much more information that you need. Thank you.
So thank you very much, Jacqueline. So it's open for time for questions. Please put your questions in the chat of YouTube, and then I'm going to read it to Jacqueline. So please do your question as soon as possible. Waiting for some questions. I have one. You talk about the designs using 7 nanometer and 6 nanometer.
Yeah, so thank you, Professor Reis, for the question. I will go back here a few slides to try to give you a little bit more on information on this, Professor Reis. So basically, we since 2017, we have been working with this technology, basically to try to meet the requirements of power consumption. So for us to design this kind of device to support these high-speed transceiver optical modules, we are talking about power consumptions in the range of 7 watts per device. The first DSP-ASICs that came out, they were consuming around 30 watts of power consumption to support applications very similar to the ones that we are doing today, that we are deploying today. So the main motivation behind of using this type of process to support this application was basically to meet the power consumption requirements that we have. But besides this challenge of power consumption, this was a new technology, and most of the flow developed and used by the industry was not so mature. And we had to work very closely with the foundry and other third-party IPs to try to understand what we could do to take the best advantage of those silicon process. But the main motivation to use this type of this technology was to meet the requirements of power consumption, and of course allow us to integrate millions of transitions in a much more reduced area. So this was the main motivation behind using this type of technology.
Yes, but which foundry are you using?
Yeah, so the foundry, unfortunately, it's a very sensitive information for us. What I can say to you is that there are not many foundries that are using this process, right? So if you take 6 nanometer, 7 nanometer, for instance, it's public information, right? That we have TSMC, we also have Samsung working in this technology. Intel was also working on this technology. And because of the non-disclosure agreement that we have with our customers, we cannot disclose this type of information. But it's basically those main founders that I mentioned before.
Okay, it's up to you, but in general, normally the companies don't worry about saying where they fabricated their chips, no? But
Yeah.
okay. So we have here a question by Professor Jacob Swart. So nice talk and impressive achievements. Is the ASIC design done completely in Brazil site and partners?
Yeah, so let me go back here a few slides. This is a very good question. Thank you, Professor Jacobs. So if we look on the flow, starting from the specification all the way to the production, we work on this flow end to end, right? So, and in terms of the design itself, when we look on the digital part of this device, all the design from the RTL logic design forward for the physical implementation is done here in Brazil with our partners. So but of course, there are some IPs that we do not develop by ourselves. Some IPs we acquired, but those IPs, they are soft IPs that we integrated inside the digital core and do all the physical design. But when we look on the physical design of the digital core and the integration with the analog, with the digital core to provide, let's say, the integrated GTS and send to the foundry, this is done here by IDEA team and partners.
Okay. Another question, if you can tell us which EDA tools are you using?
Yeah, this is a very good question. We have worked with Cadence Flow. Most of the work for design and verification, we use Cadence tools for RTL simulations, synthesis, place and route, and let's say the initial stage of the sign-off of the chip. We also use and work with other tools to do let's say, the sign-off, the end phase of the sign-off of the chip. We use Mentor Graphics. I think most of you know about Calibre, so this is the kind of tool that we use. So basically, Cadence to do the design and sign off Mentor. We also have some partners working with us to try also to develop some pieces of the flow that we are using today with Synopsys as well. But this is mainly focused for research and development. But the flow that we use today is mainly Cadence and Mentor.
Okay, thank you very much. So we have a question by Professor Altamiro Suzin. Very interesting projects, congratulations. I failed to understand your business model. Perhaps I missed something. Where the demands come from and how are the research financed? Some IP provider?
Mm-hmm. Yeah, so this is also a very interesting question. Thanks for that. So basically our business model, it relies on R&D services. All the demands comes from our partner that is based in US. So we are not, let's say, the company that sells directly the product. So basically what we do is we work with this partner to provide services, technological services, so that this partner work also together with us to build the prototypes and the end products that will be shipped to the end customers. So basically, this is how we do. We are hired to do these R&D services in photonics, microelectronics, and product engineering. We provide this technology to be matured with the same partner that we have in US, and then that's how we are funded. So, and of course, with the funding that we receive, we also used parts of this fund, this revenue, to promote R&D programs inside Brazil, such as with the University of Campina Grande, with CPQD in Campinas, with Eldorado. We hire other companies also to provide technological services as well, depending on the demand that we have, either on microelectronics, or in photonics, or in product engineering. So this is how we work.
Okay, thank you. I saw also in this slide that you are showing that you have a partnership with INFI in Argentina. I don't know if they spell INFI or INFI, but so, and by the way, INFI are going to give a talk here in 2 weeks. So as I told in the beginning, in the next. So which is the partnership you have with INFI?
Yeah, actually, Professor Reis, we don't. The intent of this slide was to show the ecosystem that is working on this kind of application. We are not partners for those companies. We have this partner here. Those companies here, they working on the same kind of application that we are working today. So Makeda is one of them that tried to also build this optical module here to tackle this demand here for the optical data, the data center, hyperscaler data center. INFI is also another company. NTT Electronics that is based in Japan. Finisar and New Photonics, along with Acacia and INFI, they are based in US. So those companies work also on this coherent technology to try to develop these optical modules to be deployed inside data centers and to promote this type of connectivity. We also have some partners in Argentina that is a spin-off company that is working there, also to help us developing some of the IPs that we used inside IDEA. Okay,
thank you very much. So I see no more questions here. So thank you again, Jacqueline. It was very nice to see your talk, the work you are doing. So wish you to your company a great success. It's very nice for us to see that you are doing a nice work based here in Brazil. And I hope that you be able to keep growing more and more and to do more designs here. So thank you very much.